Hi, this is Azmath. I'm excited to present my final project for the course Deep Learning with Neural Networks, taught by Professor Tom. This is Azmath Noorain from a student from UNT at 1010. So, the title of my presentation is Architecture Enhancements for CNN, a CIFAR 10 case study. The project explores how convolutional neural networks or CNNs performs across datasets of varying complexity. I focused on building models using TensorFlow directly without Keras to gain deeper control and understanding on the architecture. We will look at how a basic CNN performs on CIFAR10, compare it to the MNIST dataset, and then walk through the improvements I implemented to boost accuracy. Along the way, I will also touch a fish imagery dataset that's well suited for deep learning applications. By the end of this presentation, I hope to show how thoughtful architecture tuning can make a measurable difference in model performance, especially when working with a complex data. So let me start with the purpose of this project. First, I wanted to explore how CNNs behave when applied to the data sets of different complexity levels. MNIST is simple grayscale digits, but whereas CIFAR is much more complex, color images of real-world objects. This contrast helped me understand how architecture depth and training strategies affect the performance. Secondly, I used TensorFlow directly without Keras. This was a course requirement, but it also gave me a full control over the computational graph, weight initialization, and the training loops. It pushed me to understand the mechanics behind each layer and each operation. Then the third one, where I focused on improving CNN accuracy. After building a baseline model, I experienced with enhancements like normalization, then the dropout, and the learning rate decay, then generalization, the speed, also the optimizer, these change and others. These changes help the model generalize better and converge faster. So this project wasn't just about building a model. It was too about understanding why a certain design choices matter and how they impact the learning process. Yeah. This was about the purpose of the project and the introduction for this project. So let's see what's today's agenda. So here's a quick overview of what I will be covering today. So for the first topic, it will be like use of TensorFlow. I will explain why we avoided Keras and what benefits came from using TensorFlow directly. Then the next agenda will be of the day will be Fish Imagery Dataset, a unique dataset from a US Geological Survey annotated for species and individual fish recognition, and some more points on that, obviously. Then the CIFAR10 CNN architecture and its results. The basic CNN architecture which I used, I will walk through the basic CNN model I built and how it performed, the results, and then go on with understanding what are the limitations I got and how I overcome and the challenges I faced, and then from where I got the challenge ideas, how to overcome that, and then what I implemented to change that requirement. Yeah. So the next agenda of the day will be the fourth one is the CNN performance comparison. We will compare results from CIFAR 10 and MNIST to highlight how data complexity affects accuracy. Then the next agenda will be the improved CIFAR's 10 CNN. I will show the enhancements that I made and the resulting performance boost. And the last agenda will be the conclusion. I will wrap up with the key takeaways and the reflections. Each sections build on the last, showing how small architectural changes can lead to big improvements in deep learning outcomes. So, coming to the next slide, the use of first slide is first part of this project, use of TensorFlow directly. One of the core requirements of the project was to use TensorFlow directly without Keras, which was a little challenging but really interesting. Why does that matter? Keras is a high-level API that abstracts away many details. TensorFlow, on the other hand, gives you full control on how your model is built and trained. You define every layer, every operation, and every training step manually in the TensorFlow, though it's a lengthy process, real lengthy process. This approach helped me understand how convolutional layers process image data, then how pooling reduces spatial dimensions, how gradients flow during backpropagation, and how optimizers like SGD and other behave differently. It also allowed me to experiment with custom learning rates, schedules, weight initializations, and dropout strategies, all of which will be harder to fine tune in Keras. So while it was more challenging, using directly gave me a much deeper understanding of CNN mechanics and the training dynamics. So there was a question in our report asking to what the two questions. So let's answer them. So students must use TensorFlow directly coding in building train or test data CNN in the final project. So what's the answer, true or false? The answer is true. Students should only use TensorFlow. Coming to the next question. Students must not use Keras in coding in the project. Answer is true. Yes, the student must not use Keras, and I haven't used in this project. Telling you, you can see it. Coming to the fish imaginary dataset. Yeah. Before diving into CIFAR 10, I want to briefly highlight another dataset I explored, the annotated fish imaginary dataset from the US Geological Survey. So as you can see here, I specify the highlights and the source we have taken from. So this data set contains 512 annotated JSON files across 7 fish species plus individual brook trout. Each image is labeled with bounding boxes and species IDs. Yeah, making it ideal, which makes it ideal for CNN-based classification and object detection. What makes this data interesting? It's a real-world data collected using GoPro cameras under controlled lighting. It includes both species levels and individual level annotations. It uses VGG image annotator format, which is compatible with most deep learning workflows. This dataset is publicly available and ready for deep learning applications. It's a great example of how CNN can be used beyond standard benchmarks like MNIST or CIFAR 10, especially in ecological research and conversation. While I didn't train a model on this dataset for this project, I included it to show the diversity of CNN applications and the importance of well annotated data. Now, let's dive into the architecture I used in the CIFAR-10 dataset, a benchmark in image classification. This dataset, which contains 60,000 32 into 32 color images across 10 classes. It includes airplanes, cats, trucks, and frogs. Yeah. For this, the model design which I have used, the CNN architecture I implemented, it follows a classic structure. So first, the input layer, it accepts 32 into 32 into 3 RGB images, red, green, blue images. Convolution layer 1. For the convolution layer 1, 32 filters of size 5 into 5 followed by ReLU activation. I used max pooling layer, which is 2 into 2 pooling, 2 by 2 pooling to reduce spatial dimensions. Now, next coming to the convolution layer 2, as I have said, there are 2 convolution layers plus max poolings in each layer. So for the convolution layer 2, there were 64 filters of size 5 into 5, again followed by the ReLU activation function. Then the max pooling layer 2, which is another 2 by 2 pooling, which also helped to reduce spatial dimensions, obviously. Then there's a fully connected layer with 1000 and 1024 neurons with ReLU activation function. The output layer, softmax activation, there is an output layer in which I use softmax activation for 10 class classification. This architecture is relatively shallow, which makes it efficient but limits its ability to extract complex features from high dimensional data, which is this CIFAR-10. It has like high dimensional data. The training configuration in this is like I used optimizer in where the optimizer I used is SGD. It's stochasticated gradient descent, which is simple but slower to coverage. The loss function here is gross entropy, which is ideal for multi-class classification. In here, the batch size was 128, whereas the training steps which I have used in this coding is 5,000 steps, and there was an evaluation frequency for each and every steps and every 100 steps. The performance graph on the left, you can see the CNN test accuracy over training steps. Let's take a moment to interpret the graph shown here. The x-axis represents training steps from 0 to 5,000, and the y-axis shows test accuracy ranging from 0.40 to 0.70. The blue line with circular markers show accuracy checkpoints. These blue lines, yeah. The key observations in this is the first 1,000 to 2,000 steps accuracy increases rapidly. This is where the model learns basic features like edges and shapes. After 2,000 steps, the growth slowly stabilizes around 70% accuracy. The plateau here, it indicates the model has reached its learning capacity under the current setup. Why it is plateaued? So there is only limited depth with only 2 convolutional layers, and the model struggles to capture deeper spatial hierarchies. So, and also there are no regularizations. Without dropout or batch normalization, the model may be overfit or underfit depending on the data set. Depending on the data. There is optimization limitations also. SGD doesn't adapt learning rates, which can slow convergence and trap the model in the suboptimal minima. There is a data set complexity also. The CIFAR-10 is significantly more complex than MNIST. It contains color images with 3 channels RGB, increasing input dimensionality. So classes like Cats versus dogs or truck versus automobile have overlapping features. This model needs to learn texture, shape, and color patterns simultaneously. This complexity demands a more robust architecture than what we used for this basic model. These graphs and the architecture analysis help me identify the bottlenecks in the model's learning process. Next, I will compare this performance to the same architecture applied to MNIST, a simpler dataset, and highlight the differences in the accuracy and convergence. Let's go to the next slide. So, now we are now we are comparing the CNN versus MNIST performance. Here's a slide. MNIST results were like in the project which was our course project. We got we achieved 98.3% of accuracy. It was really good. In that the grayscale digits are simple and uniform. The model coveraged quickly and performed exceptionally well. So CIFAR 10 results originally reached 65.1% accuracy. The model struggled with color complexity and class ambiguity. Coverage was lower and accuracy plateaued after 4,000 steps. Yeah. The key differences between MNIST and CIFAR is like MNIST has 28 into 28 into 1 grayscale, low dimensionality, whereas CIFAR 10 32 into 32 into 3 RGB, which is really higher dimensionality. CIFAR 10, which made CIFAR 10 requires deeper networks and better regularization. Yeah. So now this comparison highlights how dataset directly impacts CNN performance. A one-size-fits-all architecture doesn't work across all the datasets. So I decided to improve the CIFAR 10 model by enhancing its architecture and training strategy. So now in this slide, we will see how improvise CIFAR 10 CNN. So after I'm analyzing the limitations of basic CNN, I implemented several enhancements to improve performance on the CIFAR data set, which was a real successful story. Thank God. Yeah. So the architectural improvements. Here's I'm gonna tell you the model overview. What are the breakdowns I have changed? First is batch normalization. After I added the normalization batch wise after each and every convolutional layer to stabilize the learning and reduce internal covariate shift. Then I increased the dropout. In the previous basic one, the dropout was 0.25, so I increased by 2.5. I increased regularization to prevent overfitting, especially in the fully connected layer. I observed there was an overfitting in the data set, in the model. That's why I had to do this. Then for the optimizer, I switched from SGD to Adam, which adapts learning grades dynamically for each parameter. Yeah. Then I also added weight initialization. Instead of the default weight initialization, I use Xavier Glorant to ensure balanced gradient flow across layers. Then the learning rate decay. I implemented learning rate decay exponentially to fine-tune convergence in the later stages. I also did the data normalization. I scaled pixel values to the zeros and ones range, 0 to 1 range for more efficient training. These changes were designed to improve generalization, accelerate convergence, and extract deeper features from the data because it's a complex data. Then let's see the graph on the left side. This is the performance graph. Improved CNN accuracy over training steps. So let's look at the graph and show that shows how the improved CNN performed during the training one. So the x-axis represents training steps from similar to the previous ones, training steps from 0 to 5,000. Yeah, for this improvised CNN also, I used the batch size was 128 and the training steps were all 5,000, similar to the previous one. So for the coming back to the graph, the x-axis represent training steps from 0 to 5,000. The y-axis shows test accuracy, ranging from 40% to 80%. Before it was 40 to something, 70 to 75 something. Now it's 40% to 80%. Yeah. The line chart shows a strong upward trend with the accuracy climbing rapidly in the first 1,000 steps, which was the same in the previous one because it sees the shapes, sizes, and the edges of the data. After 3,000 steps, the model begins to plateau around 77 to 78 accuracy above all. The previous graph, it was at 68%, whereas this graph is at like 77.65, 77 to 78% accuracy. Yeah. So the key insights we can see from this that this model learned faster and more efficiently than the basic CNN. The plateau is higher, indicating better generalization and deeper feature learning. The graph is a visual confirmation of effectiveness of the architecture enhancement. So the final result summary will be like final test accuracy is 77.65 percentage. Improvement over base models was like 7.85 percentage points. Training steps were 5,000, which I have told you again. Coverage and speed was faster and more stable. Generalization stronger with reduced overfitting. Why this worked? Batch norm allowed higher learning rates and stabilized training. Adam Optimizer adjusted learning rates dynamically, improving convergence. Dropout reduced overfitting, especially in dense layers, whereas the learning rate decay helped the model settle into optimal weights gradually. Together, these enhancement created a more robust and efficient CNN, capable of handling CIFAR 10's complexity. Next, I will show a side-by-side comparison between the base and the improved CNN models to highlight the architectural differences and the performance gains. The comparison. So this table summarizes the difference between the basic and the improvised CNN. So architectural depth, basic one had two convolutional layers with one fully connected, whereas the improvised one has two connection layers with batch, normalization, and dropout. So optimizer and learning strategy, basic one has SGD with fixed learning rate, and whereas in improvised I used Adam with exponential decay, regularization and initialization. Basic one had dropout 0.25, which was default in it. But for the improvised, I increased a little bit for like from 0.25 to 0.5. So like with the help of Xavier in it. Yeah. Performance metrics. So the accuracy jumped from 69.8 percentage to 77.65 percentage, which is a real big jump. Generalization improved, coverages speed increased a lot. So for this, both I use the training steps were like 5,000. The loss function was cross entropy for both of them. Data pre-processing for basic CFR, basic CNN, where we use raw pixel values. Whereas for the improvised CNN, I normalized them from the raw pixel values to 0 and 1s, which helped us in making things easier. So generalization, it was moderate, whereas in moderate in basic one, whereas in improvised it was like really strong. The coverage speed was lower in basic, whereas in improvised we had a faster coverage. So the conclusion and the key learnings for this whole project. Let's wrap up with some things. To conclude, here are the key takeaways from this project. TensorFlow's low-level API gave me full control over model design. First, this was the first point. Yeah, because of not using Keras, I had the full control on TensorFlow's low-level API, which I enabled when using the GCP protocols in the GCP. Yeah. Data then comes data complexity matters. Shallow CNN works for MNIST, but not for CIFAR 10. For CIFAR 10, we had to use improvised version when compared to MNIST. So each model have, as the dataset varies, as the dataset complexity varies, we need to change the model or how we are modeling. So architecture tuning like normalization and dropout can dramatically boost performance. Like normalization and dropouts. So the learning outcomes from this, I gained hands-on experience in building and optimizing CNNs. I learned how to diagnose model limitations and apply targeted improvements. I saw firsthand how hyperparameters and training strategies affect learning dynamics. Yeah. Now, for future work, how it can go is like explore. We can explore deeper architectures like ResNet. We have other architectures too. We can also apply augmentation and also early stopping. Will that work? Yeah, early stopping. Yeah, and then we can also experiment with transfer learning for better generalization. Yeah. Thank you for listening and for your time and attention. I would be happy to answer any other questions. This is one side presentation. I don't think we have, but you can surely answer in down the video for this YouTube link. Thank you.